Thank you. Thank you very much for the invitation and for opportunity to give this presentation. So in the title, I have two topics, and really this talk is about an idea how to combine the study of vortex equations with a problem in algebraic or symplectic geometry of counting holomorphic curves. And this is very much work in progress with in collaboration with Thomas Walpuski. And some of the results I will state are also in collaboration with Eleni Ionel from Stanford. And as I said, this talk is really about two things, but I will talk a little bit about some older work, mostly on the holomorphic curve theory side, but I hope towards the end of this talk, I can get to the gauge theory equations, which is, of course, what's more relevant to the topic of this conference. But let me begin with this very classical problem in algebraic geometry, and that is the problem of counting complex subvarieties. So what's the very general setup? I give you some projective manifold X, and I can ask how many holomorphic curves, so complex submanifolds of dimension 1, are inside this complex projective manifold. And usually for this problem to make sense, I need to prescribe some data about my curves. So for example, I will say how many curves of given genus, given degree, and maybe some additional constraints such as these curves should be passing through some points or other subvarieties or satisfy some tangency relations. And this is something very classical that goes back to, Italian school of algebraic geometry or people like Schubert and Grassmann in the 19th century. So this is very much at the core of classical algebraic geometry. And here are some famous examples. So if you give me 2 points in CPN, then there is a unique line. So a genus 0, degree 1 curve passing through them. If instead you think about the surface in CP3 defined by cubic equations, and another classical result that there are 27 lines lying inside, containing that cubic surface. And this is a more less classical, but 20th century computation. You could take the quintic threefold, so the zero set of a quintic polynomial in CP4, and you can ask how many lines lie in it, and also curves of higher degrees. And this is a very famous computation that started this entire story with mirror symmetry and got string theorists interested in that. And the very famous number is 2,875. And of course, if you consider curves of higher degree, that there's an entire story how to compute these numbers using mirror symmetry. So let's be a little bit more precise about this problem of counting curves. So I fix my projective manifold X, and I fix some second homology class A, and I fix some genus G. And I can look at the so-called moduli space of curves. So essentially the space of all holomorphic curves of that genus G, that homology class A. And it is some topological space, not necessarily a manifold, but if you count how many degrees of freedom you have minus how many equations you have to satisfy, you come up with an expected or virtual dimension of this space of curves of given genus and given homology class, and is given by this formula. So there's a dimension of X, the genus, and the pairing of the first Chern class of X with this homology class. So what do I mean by counting curves? If this number happens to be 0, then I expect to have a 0-dimensional moduli space of curves. And if things are good, this 0-dimensional space is just a bunch of points and a finite number of points, and I can count them. And that's what I mean by the count of curves. If the virtual dimension happens to be positive, then I need to impose some conditions on my curves, such that this curve should pass through certain fixed points to kill the dimension to 0. And a very nice case, as you can see from this formula, is that of Calabi-Yau threefolds. So if the complex dimension of X is 3, and the first Chern class pairs with the homology class to 0, in particular if the first Chern class is 0, then there is this peculiar feature that the virtual dimension is 0, no matter what homology class and what genus you choose. So that tells us that the curve counting theory on Calabi threefolds is very special because of this property. Because all virtual dimensions are 0. So if we want to make this curve counting problem more precise, we actually would want to say, take this moduli space, which is a virtual dimension 0, show that it's a finite number of points and count these points. Well, this doesn't actually work this way because of 2 issues. First of all, the transversality issue that the modular space of curves doesn't actually have to be a manifold of the virtual dimension. In the same way, if you have a 0 set of a function doesn't have to be a submanifold for the same reason. And then there is a second issue of compactness, that even if you're interested only in counting these embedded submanifolds or maybe mildly singular ones, they can actually in families degenerate. And that is a famous problem in this theory, that depending on what sort of generations of curves you allow, you get a different answer for what it means to count curves. So one way of overcoming these 2 difficulties is to extend the class of manifolds you consider, and instead of considering projective manifolds, you allow a more general class of manifolds with non-integrable almost complex structures. So let X and omega be a symplectic manifold, and we can always find an almost complex structure on this symplectic manifold, which is compatible with the symplectic form in the sense that the contraction of the symplectic form in this almost complex structure defines a Riemannian metric. So such a triple we call as symplectic manifold with a compatible almost complex structure. And in fact, there's an infinite dimensional space of these J's, and this space of compatible J's is contractible, as shown by Gromov. So in some sense, there are many choices, but the choice up to homotopy is irrelevant. So then the idea is that instead of looking at holomorphic curves, you can look at a more general class of solutions to this nonlinear Cauchy-Riemann equation. So you look at maps. Let's say sigma is some Riemann surface. You look at maps, smooth maps whose derivative is J linear with respect to this almost complex structure. So here, small j is the complex structure on sigma, capital J is the almost complex structure on the symplectic manifold. And this is a nonlinear generalization of the Cauchy-Riemann equations. So you can look at the space MGA xj. So this is the moduli space up to reparametrization of all maps satisfying this equation, such that G is the genus of your Riemann surface, and these maps represent the homology class A in X. And this is the moduli space of pseudo-holomorphic maps. And in particular, an important property that all such maps are harmonic. In other words, their image is a minimal, it minimizes volume area in its homology. So of course, we recovered the previous setup by considering J to be an integrable complex structure and U being an embedding of a holomorphic curve. But this setup has the advantage that it can deal with both of these issues that we discussed. So the first issue was the transversality, that the moduli space is not necessarily of the right dimension. Well, now, because we have a large infinite dimensional space of all possible almost complex structures, we can wiggle the almost complex structure to make the moduli space, at least a big chunk of it, a manifold of the right dimension. So this is the flexibility that the integrable case didn't allow, because there is only a finite dimensional space of deformations of complex manifolds, but the space of deformations of J is infinite. So that solves the problem of transversality to some extent. And then the second issue was that of compactness, and that is a big contribution of Gromov and Kontsevich which in some sense goes back to work of Uhlenbeck and Sachs on harmonic maps, that there is a reasonable compactification of the moduli space of pseudo-holomorphic maps. And this is the so-called moduli space of stable maps, which are pseudo-holomorphic maps where you allow the domain of your map to degenerate to a nodal Riemann surface. So maybe you started with maps from smooth Riemann surfaces, but they could degenerate to maps from nodal Riemann surfaces, and you allow maps like that from surfaces like that to X, which satisfy the stability condition, and also that they are J-holomorphic on each component. And then you put all of these into a big moduli space, and Gromov's compactness theorem says that this is a compact space with appropriate topology. So that allows you to embed your space of curves into a compact topological space. This space is not a manifold, and in general can be quite singular, but there is a complicated procedure that I don't want to discuss that allows you to extract numbers from this moduli space. So when, in the case we are interested in, when the virtual dimension is 0, this leads to Gromov-Witten invariance, which in some sense is some sort of virtual count of points in this singular space. And what you show that as you choose different J's, you have something like a singular cobordism between these two moduli spaces. And that shows that the count, this cobordism allows you to prove that the count of points, the virtual count of points in this moduli space is independent of J. As you remember, this space of all possible J's was contractible. So in the end, it doesn't matter which one you chose. You can show that this number, the Gromov-Witten invariant, does not depend on J. It only depends on X, the symplectic form, genus, and A. And these numbers are integers, are not integers, they are rational. And this is because when you do this virtual counting procedure, you have to take into account that some curves have symmetries. So this is something I'm going to discuss now. So the upshot is that you get this nice invariant of a symplectic manifold, but it's very hard to say what exactly this invariant is counting. It certainly is not counting embedded holomorphic curves. So it's something that's related to this classical problem algebraic geometry of counting curves, but it's not exactly that. And the one way to see this is that once you compactify this moduli space, the price you're paying is that this space has plenty of maps in it which are not embeddings of pseudo-holomorphic, not pseudo-holomorphic embeddings. So one way to see it, if you have a pseudo-holomorphic embedding from sigma to X, you can always compose it with a branched cover of Riemann surfaces, and the composition is again pseudo-holomorphic. And that composition is not an embedding. And in fact, because there is an entire higher dimensional space of branched coverings, you have an entire large chunk of the moduli space consisting of such multiple covers, but the image of all of these covers is the same curve in X. So somehow geometrically, a single curve can contribute to a big chunk of the moduli space by this procedure. And similarly, because now we are allowing maps from singular domains, you could have a single holomorphic curve. So for example, a single sphere inside X. Even if this one is embedded, now what I could do, I could consider this singular Riemann surface and look at the map, which is constant on this component. Such maps are called ghosts. So now I get the map from a higher genus Riemann surface whose image is a lower genus surface. And again, because I have the freedom of attaching this point and I have a freedom of choosing the complex structure on this Riemann surface, I get an entire large dimensional chunk of the moduli space, which definitely does not consist of embeddings. And all of these guys that I'm describing have a contribution to the Gromov-Witten invariant, So definitely the Gromov-Wood invariant is not just the count of embedded curves. Just give me a moment. I want to turn off the sound for the chat. Okay. So that leads to the natural question. We have these beautiful Gromov-Wood invariants that are computable. This is, of course, a very well-developed and famous theory, but we can ask, are there some invariants like the Gromov-Wood invariants, which in some sense count embedded to the holomorphic curves as opposed to these stable maps? So that have a more natural geometric interpretation. So in particular, one thing I already said, let me go back to it, because you have to incorporate contributions from multiple covers, Gromov-Wood invariants always end up being rational. I mean, not always, but typically tend to be rational numbers. So in particular, we could ask, is there some invariant that we could actually interpret as a count of some embedded curves, possibly with some decorations, so maybe curves plus some. And there are such invariants. Well, first of all, let me say that in some special situations, the Gromov-Wood invariants actually do that. So the numbers, for example, for the quintic threefold that I was giving to you, this is the count of curves, but it's also the Gromov-Wood invariants. So it's an interesting question. When are Gromov-Wood invariants enumerative? And it does happen sometimes. And then in a more general setting, for symplectic manifolds of dimension 4, there is also an invariant defined by Taubes, which essentially counts embedded pseudo-holomorphic curves, except that some of them you have to count with certain weights. And finding these weights was a big idea that Taubes had. And moreover, he showed that these invariants, these curve counting invariants in dimension 4 are equal to the Seiberg-Witten invariants defined using H3. So we could ask, is there something like that in higher dimensions? So let me state the first theorem in collaboration with Tomasz Lotpuski. So this is a theorem that naively tries to answer the question if there is some setup in which we can talk about counting embedded pseudo-holomorphic curves. So the setup is this. We have a compact symplectic manifold whose real dimension is 6, so complex dimension 3, and the first Schoen class is 0. So this is like a symplectic analog of the Calabi-Yau condition, the Calabi-Yau threefold. And let me just say that, in fact, there is a generalization of this theorem that deals with arbitrary symplectic 6 manifolds. It's very similar to this one. It just for simplicity, I'm assuming this Calabi-Yau case. And then this theorem says that for a generic almost complex structure J, which is compatible with the symplectic form, there are finitely many embedded pseudo-holomorphic curves in every homology class A. Moreover, if this homology class A happens to be primitive, then the signed count of these curves of this homology class is genus G is independent of J and is a symplectic invariant. So by primitive, here, what I mean is that A is not equal to dB for D an integer and B in integral second homology. So of course, most classes are not primitive, but this is what it means to be primitive. So this is an example of a very special setup where you can naively choose a generic, almost complex structure. Generic meanings from some from some dense set in the space of all almost complex structures. Then you get finally many embedded pseudo-holomorphic curves, and then you can count, and that defines an invariant. So in particular, one thing I want to stress here that in this theorem, so in this statement that there are finitely many embedded pseudo-holomorphic curves, we do not specify genus of these curves. And the reason I'm saying that, because if you go back to what I said earlier, there is this beautiful Gromov-Witten theory, and part of it is the Gromov compactness theorem, which says that the moduli space of stable maps of fixed genus is compact, and fixed homology class is compact. And this is the foundational compactness result in this theory. But at the very basis of this result is that we look at space of maps from surfaces of given genus. So Gromov compactness cannot tell you anything about what happens to these curves as you vary genus. And as a result, you cannot use Gromov compactness or anything like that to prove this theorem, which is some statement that is independent of the genus. And instead of using these classical tools of symplectic geometry, what we use here are some results from geometric analysis, and specifically from geometric measure theory. So are there any questions at this point about what I said or about the statement of the result?
If you fix the genus, then is this easy? Like, is the difficulty of the, where does the difficulty of the result come from?
So if you fix the genus, you
Like,
still have to worry about, right. So if you fix the genus, you still have to worry about the fact that you could have a sequence of curves that collapses either to one of these singular. So you could still have an infinite sequence of curves potentially that can collapse to one of these multiple covers or one of these ghosts.
but then you said it's a primitive class, so the multiple covers doesn't happen, right?
Yes, so sorry. So there are two parts of the theorem. So yes, so if you are primitive, then the multiple cover collapse doesn't happen. It can still happen that there is a collapse to the ghost. But here, this actually statement, the first time is independent of the class being primitive. So in this case, you could have both. But I believe that if you fix the genus, you could prove, for the fixed genus, you could prove this result using Gromov compactness and tools from pseudo-holomorphic map theory. The similar tools to what I'm gonna discuss.
Okay, thanks.
Somehow for the purpose, this genus thing this is how we got interested in it, because later I will talk about trying to define some invariants that are known from algebraic geometry that are agnostic to the genus of the curve. So they don't want to specify the genus. Notably, Donaldson-Thomas invariants and their variants, then they do not care about the genus of curves. So the motivation for us was to try to find a symplectic analog of these things. And in particular, we wanted to have a compactness theorem that doesn't rely on the genus. But yes, I think if you fixed the genus here, you could try to prove, you still have to worry about this collapse, but you could rule it out using just Gromov compactness and the known results in pseudo-holomorphic curves map theory. So let me just very briefly discuss the idea of the proof, just to show how it's different from some of the standard things you do in the study of moduli spaces of pseudo-holomorphic maps. So this is just a very brief sketch. So it's a combination of some results in geometric analysis and some result about pseudo-holomorphic maps. So the first step, you choose a generic J, and you can show that the moduli space of curves, meaning the moduli space of simple maps, so not multiple covers and not singular guys, is discrete. And because we're in dimension 6, you can show something like, it's something like Whitney embedding theorem, essentially, that shows that all of these simple maps are going to be embeddings, and they're going to be pairwise disjoint. But what could happen is that there are infinitely many of them. So you could have So you have, if you think of the moduli space of these embeddings, some kind of accumulation could happen. And of course, then you don't have a finite number of points. So by contradiction, we assume that it indeed happens that you have an infinite sequence of such curves in prescribed homology class, not necessarily prescribed genes. So then the point is that if you have a map, if you have a curve inside X, you can think of it as a functional on the space of two forms. So as a current, because you can take a form alpha and integrate it over a surface. So then you think of these cycles, think of these curves as currents. You put them in the space of currents with weak convergence of currents topology. And you can use Federer's compactness theorem to show that these currents must have a limit in the space of integer rectifiable currents. The limit could be quite a horrible thing in general. But you can use some of the work of the Lelis, Spadaro, and Spalora, inspired by Almgren's work on regularity of minimal submanifolds, to actually show that the limit current is not some arbitrary bad current, but it's actually something very nice. It's going to be a formal sum of their Dirac deltas, certain that some curves with integer weights. And now, because all of these guys are going to be images of pseudo-holomorphic maps, by step one, these CIs are actually going to be embedded and pairwise disjoint. And since we assume that we started with connected thing, a posteriori you can conclude that actually, because these guys were embedded and pairwise disjoint, there must be only one of them, because we started with a currents that have connected support. So in the end, we'll get a current that's connected support. So we conclude that the limiting current is something like just a Dirac delta centered at C, some holomorphic curve that we don't know, times M, and in a positive integer. So we want to arrive at the contradiction. And here is a nice idea that was used by Taus in dimension 4. So you have this limiting thing. And before, you had a sequence that C1, C2, and so on, that converges to that one. So of course, as n goes to infinity, the sequence Cn converges to MC as current. So in particular, it gets closer and closer to C. So what you do, you take the normal bundle of C, and you start rescaling all of these guys so that this distance is 1. So I look at new Cn tilde, which is rescale Cn, so that the Hausdorff distance of Cn tilde and C is 1. Even though the original, of course, the original distance going to 0. And now you can do this again, this trick that Cn is now a sequence of currents that have bounded area. So again, you, after passing to the limit, you get that there is a limit which is of the form some other m, maybe n, times some C infinity twiddle. So this is the same argument that gives us the limit of this guy. Actually, I just called it C twiddle, sorry, in this. So in the end, you get this limit C twiddle, and you can show that because the original curves were pseudo-holomorphic, in the limit, you get something like a graph of a multi-valued pseudo-holomorphic section of the normal bundle. So here, everything was happening in the normal bundle of C. And you can show that this limit is going to satisfy a certain PDE. And now you think about what is the meaning of this PDE. And the meaning of this PDE is it's something like infinitesimal deformation of a multiple cover of C from the viewpoint of the deformation theory of pseudo-holomorphic maps. And now you look at the PDE it satisfies, and you see that the index, it's a PDE whose index is negative. So you don't expect to have any solutions to that generically. But actually, to prove that, it's a very non-trivial statement, and this is exactly the content of the superrigidity conjecture that was a few years ago proved by Chris Wendell, that these multi-value pseudo-holomorphic sections cannot generically exist because they have to satisfy a PDE whose deformation theory is governed by a negative index elliptic operator, and there is some work in showing that generically, indeed, such non-trivial solutions cannot exist. So by combining this new result, we get the contradiction, which shows that, of course, our original sequence of curves couldn't exist. So there must have been finally many to begin with, as long as we chose this J carefully to be sufficiently generic.
But in your case, you are considering a primitive class. So why does all of this matter?
I'm not considering a primitive class. So this, I should have said that there is a part A and part B here.
All this you did is for the proof of part A.
Yeah, so I was discussing part A. But even in the primitive class case, it still could happen that even if the multiplicity is, so it could still happen that even if this multiplicity is 1, what could happen, for example, that this limiting curve has a different genus than the original curves, because I'm taking a limit as currents, so which does not, in general, preserves the genus. But in any case, I was just discussing class statement A for now. So the statement A doesn't require that that the homology class is primitive. Does that make sense? Yeah, I should have been clear. I'm sorry. So I'm talking now about the statement A, and then there is this extra statement B that if the class is primitive, then the count is an invariant. I was just addressing the finiteness property. Okay. So this is how you prove. I see. So this proves the part A, that there are finally many curves for a generic J, no matter what genus. So now I just want to say why the count is independent of J. So you could understand it by looking at this proof that I was discussing. So when does the proof fail? The proof I just discussed. Sorry. The proof fails when I get some pseudo-holomorphic curve in the normal bundle, which equivalently corresponds to the graph of a multi-valued pseudo-holomorphic section of the normal bundle. This is when the proof fails, and of course, this cannot happen in the for topological reasons in the primitive case. That's essentially the upshot. You still have to worry a bit about the collapse to the in the same homology class, you could have a collapse to a ghost map, because the ghost map, so you could have, for example, something like that, collapsing to a map like that, where the map, all of the energy goes here. So this is non-constant, and this is constant. So you still have to worry a bit about this, but okay, you can rule this out with some extra work. But the main property is that we lose some of these embeddings can degenerate to multiple covers, and somehow the primitive condition rules that out. So here is a picture of how, a cartoon of how this can happen, taken from a, so this illustration of a paper of Pandaripan and Thomas. If you have A equals MB, for some homology class B with M greater than 1, then a sequence of pseudo-holomorphic curves in the class A can collapse to an M-fold branched cover of a curve in the homology class. And the way you can detect it, as in our proof, you could look at the normal bundle of this curve C and before the collapse, if you start rescaling, you will see that you have some two, say, m-valued, something like that, like an m-valued section of normal bundle which satisfies a pseudo-holomorphic map equation. So this m-valued section remembers the infinitesimal dimension from which of this collapse. So in this picture, is m is 2 in this picture. Okay, and then essentially what I said, that if the class is primitive, that doesn't happen, therefore you get an invariant. So the option is that you always have finitely many curves for a generic J, but somehow in a family, if the class is not primitive, in a family, you can't have this collapse. You can have this collapse to a multiple cover. So I said that for a generic J, such a multi-valued pseudo-holomorphic section doesn't exist, but in a family it can exist. And that would causes these numbers NGA not to be independent of J for a general homology class. Okay, any questions about this? Let's see how, okay, so I wanted to say something. There's this digression about the Gopak-Marvafa conjecture. So let me just not talk about this now. Maybe if there are questions about this, because that will take some time. So essentially the upshot, maybe just one thing I wanted to say, the upshot is that these sort of techniques, I was really stressing that these results are independent of the genus, and these sort of techniques can be used to prove some other results about the structure of the Gromov-Witten invariants. Essentially, let me just say one sentence about this and I'll move on. So essentially, Gromov-Witten invariants are typically going to be non-trivial in every genus. Because of this, because as what I said earlier, that a single curve, no matter what genus, contributes to Gromov-Witten invariants of higher genus by this procedure of either looking at the ghost maps or looking at multiple covers. So then people were trying to understand, okay, is there some structure in the Gromov-Witten invariants that doesn't have this property? And there was this conjecture that if you repackage Gromov-Witten invariants in terms of some other numbers, the Gopak-Marvafa invariants, then they will have the property that for high genus, they are 0. And this is essentially using these techniques, because these techniques I was mentioning are independent of the genus. You can actually show that. So that's the only thing I want to say about this. But this is a digression. So let me, because I want to talk about these vortex equations. Let me go to the second part. So I said I said earlier that what you can show is that if you take a Calabi of threefold, give me genus, give me a homology class. If that homology class is primitive, you can actually count embedded pseudo-holomorphic curves in that homology class and that genus. This is an invariant. This is in fact not a new invariant. It's one of these Gopak-Marvafa numbers that I was just saying. But then I said that because of this collapse to multiple covers, you cannot get an invariant like that just by naively counting curves. So let's focus on covers of degree 2, just for the sake of simplicity. So let's take A, which is not primitive, but is of the form 2B, where B is a primitive class. So what that means is that I can choose a generic almost complex structure, J, and I know from the theorem I just said that there will be finitely many embedded pseudo-homomorphic class in the homology class A for this generic J. I could count them, that gives me some number, but this number is not going to be an invariant, because as you vary J in a family, some of these embedded curves in class A could collapse to twofold covers of curves in the class B. And that the fact that that collapse happens tells you that in a family of almost complex structures, you the number of embedded curves in the homology class A will change. So we can ask, can we correct this naive count to actually get something that is an invariant? So the most general form would be a sum like that. Again, I'm only thinking about classes that are divisible by 2, but not by any other number. In general, the story will be more complicated. So we're looking for an invariant of the following form. Let's fix A, and let's look at the generic almost complex structure J on my symplectic 6-manifold X. Now I want to have one term, which is the count of embedded curves in the homology class A, possibly with some weights depending on J. And I want to have another sum, which is the count of embedded curves in the homology class A divided by 2, which is B, possibly with some other weights depending on J. So now I assume that I have this situation that I was describing earlier, that I vary J in a one-parameter family. So I have some J0, J1, and I want to count the curves here and count the curves here, so possibly with these weights. But as I vary my J, some of these embedded curves could, there's no good way of writing it, but like could disappear. Why? Because this can happen only if I have a sequence of curves, C, twiddle, T, which as T goes to some special time, converges as currents to 2 times C, where CT, twiddle, has a homology class A, and C has homology class B. So that curve of homology class B was just always existing, assume. This is a typical situation. The curve of the homology class C wasn't created. It always existed for every J. So as I go from J0 to J1, the curve in the homology class B, nothing happened interesting to them, to it. But what happens is that it's in the homology class A, the curve disappeared by degenerating to multiple curves. So this is the setup that I'm describing here, that you could have C twiddle converging to 2 times C, where C twiddle is A and C is B. So if we look at the count here and want it to be the same, what did we lose from our count? Well, we counted this guy with weight W1 C twiddle J0, but this guy disappeared. So before we had it and after we don't have it. So that has to be compensated in the weight we attach to the curve of homology class B. So somehow this weight should depend on J, and it should be so that the difference before and after compensates for this number. So we have the task of finding weights that behave exactly in this way. So in order to do it, we have to understand why is it that this collapse happened. This curve C was just living happily from 0 to T, nothing happened to it. So why is it that suddenly this guy happened? And this is because exactly of this existence of a multi-valued, two-valued holomorphic section of the normal band. So this is what I say here, that this degeneration happened at the time when there exists a two-valued J holomorphic section of the normal bundle. So I have my curve C in the class B that happily existed for all times. It has a normal bundle, but as I vary JT, the germ of the complex structure on that normal bundle changes. And therefore, for some J's, there will be sections, holomorphic sections of the normal bundle or multi-valued holomorphic sections, and for some other J, there won't be any such sections. So the point where this collapse happens is exactly when there is such a section. And another way of looking at the two-valued section of the normal bundle is to say that this is a section of the second symmetric product. So we want this weight W2 to be something, some integer that jumps exactly when there exists a two-valued section of the normal bundle with respect to the germ of the almost complex structure. So I think there was, let's see, sorry. There was one more slide. Oh yeah, here. So there is a problem of finding these ways that jump in this prescribed way. And actually what was a big inspiration for us was that there is a similar problem that was studied in G2 geometry and spin 7 geometries with special holonomy, following all the ideas of Donaldson, Thomas, and Siegel. So the upshot of this story is that you start with some 7-dimensional manifold with special holonomy, and you want to count, rather than holomorphic curves, you want to count calibrated 3-dimensional submanifolds, so in particular minimal 3 manifolds embedded inside that 7 manifold. And then when you try to understand the generations of such manifolds, you run into a similar problem that we found, that the count of embedded 3-dimensional submanifold is not going to be invariant because of various collapses. And then Heidis and Walkuski proposed that you could, instead of just counting the 3-dimensional submanifolds, you could count them together with some weights, which themselves are counts of certain non-abelian Seiberg-Witten equations. And then they had an argument, a conjecture that the total count of 3 manifolds together with the solutions to the non-abelian Seiberg-Witten equations will be an invariant. Precisely because the number of these solutions of non-abelian Seiberg-Witten equations will jump exactly when you have 3 manifolds collapsing to multiple copies. So of course, what you can do, you can take a Calabi-Yau threefold multiplied by R. This is a 7-dimensional G2 manifold, and you can look at holomorphic curve times R, and that's a 3 manifold in it that satisfies the relevant PDE. So in fact, the entire holomorphic curve theory of Calabi-Yau threefolds is embedded into this higher dimensional story. And you could look at their proposal and reduce it by 1 dimension to get some proposal for the appropriate weights that you need to put on your curves. And it turns out, if you write it down, that what you want to do, you want to define these weights by counting certain solutions to vortex equations. So I'm not going to write all the details, but essentially it's an interesting system of vortex equations that has 3 sections, and they satisfy some algebraic condition and a curvature condition. And this curvature, a curvature equation is like a mixture of the Hitchin equation. So it has this commutator part and the usual vortex equations, which is where this part is coming from. So it's the curvature plus some Hitchin term plus some classical vortex equation term. And essentially the conjecture is that you should be counting solutions to these equations, and the count of solutions should not be an invariant, because observe that there's an important thing here, that this del bar operator depends on the germ of the almost complex structure in the normal band. And that the number of these solutions should jump exactly when you have a multi-valued section of the normal band. So this is the point I want to explain now. Without going into the details of these equations, I just want to argue why such equations, why this is a reasonable thing to look at. So the important observation here, important part of the setup is that this Xi is going to be a section of the normal bundle tensor the endomorphism bundle for some rank 2 vector bundle on the curve. And A is a U2 connection. Let's forget a little bit about this alpha and beta. So maybe just for the sake of this talk, let's just forget about these parts. So this looks really very similar to the Hitchin equation, except it's twisted by this normal bundle here. So now we could imagine, okay, let's look at the moduli space of solutions to these equations, and let's try to count them. So the count will depend on J, because this operator depends on J. So you could ask, when does it happen that the count changes? And the only way it can change is when some of the solutions escape to infinity. So what could happen is that you have a sequence of solutions. Let's again forget about alpha and beta. You have a sequence of solutions such that the L2 norm of psi I goes to infinity. And this is how the only way the number of solutions can change. This is what I wrote here. So again, alpha and beta don't really matter very much for this story, but psi can go to infinity. So what we can do, we can look at these equations and rescale them, rescale this section so that it has L2 norm 1. So I can look at psi hat, which is psi divided by the L2 norm of psi. So, and I call epsilon 1 over the L2 norm of psi. So now if I want to write these equations as equations for psi hat, well, these just stay the same. But here I'll have to put epsilon squared. So if I want to understand the non-compactness phenomenon for these equations, I have to take epsilon going to 0. And by the way, this is something that was the study of non-compactness for these various gauge theory equations like this is something that was done by Taubes and later developed by other people. So there's a very beautiful theory of studying these sort of equations. In any case, when we take the limit epsilon goes to 0, we get this system of equations. So let's see what that tells us. Well, N is a rank 2 bundle. So essentially, I have at every point 2 matrices. And these 2 conditions tell me that these matrices commute and that they commute with their conjugate. So that means that they can be simultaneously diagonalized. And what I can do, I can look at its eigenvalues, which are now, at each point I have 2 eigenvalues, which are now elements of the normal bundle. So I have my curve, I have my normal bundle, and the eigenvalues give me 2 points at every point of the curve. So in the end, I get something like a 2-valued section of the normal bundle. So this heuristic non-rigorous argument shows that you expect the number of solutions to these equations to jump exactly when you have a 2-valued section of the normal bundle. But this is exactly what caused the collapse to the twofold cover. So the summary is that the same type of object, this guy, causes 2 different jumping phenomena. One for the embedded pseudo-normative curve and another for these exotic Hitchin-like vortex equations. So you can summarize it in this following conjecture. This is current work in progress with Mansell-Puski. So of course, there are high rank analogs of these. And what we want to do, you take a homology class that possibly has many divisors. You look at all possible divisors, and you count embedded curves in all of these divided homology classes with these weights, which count solutions to these higher rank vortex type equations, which depend on J. And then you want to show that this sum is actually independent on J, because the weights are designed in such a way that they compensate for the jump in the number of holomorphic curves. And there is another part of this conjecture, which actually is, I think, much more difficult, is to show that when you actually start with the complex projective threefold, then this procedure recovers a well-known invariant in algebraic geometry that was defined using sheaf theory. And the reason we think that this is true is that you can do some local models or local computations, and you see that the solutions to these exotic vortex equations correspond to some sheaves that algebraic geometers use to define these so-called Pandari-Pandey-Thomas invariants. So in the end, you would get some invariant that would be a symplectic analog of these sheaf theoretic invariants in algebraic geometry. So there, I wanted to say just this is an interesting question in its own right to study these vortex equations and to study non-compactness phenomenon. And this is something that recently there's been a lot of progress on these sort of compactness questions due to Taubes, Heides-Walpurski, and Walpurski-Zhang, and also other people. There are a lot of interesting questions, not only from gauge theory, but also from geometric measure theory on controlling singularities of solutions to these equations and so on. So this is a very active area of research, and I'm optimistic that these new methods will actually allow us to prove parts of this conjecture. So let me stop here, and thank you very much for your attention, and I'm sorry for going a bit over time.
Questions? Questions from the online attendees?
So
There's a question here.
yeah, this may be irrelevant, but I'm curious to know the invariant, the symplectic invariant that you define in the first part. So I mean, if I want to calculate them as like numbers, are they feasible?
You mean what I just discussed, the PT invariant?
No, the first one, that symplectic invariant for.
Oh, just for the primitive class?
Yes, yes, yes.
I would think so, because yes, I mean, if you give me some, I mean, it's somewhat similar to the idea, the question of if you can compute the Gromov-Witten invariants.
Yes, exactly.
These should be actually easier because you don't often when you compute. So I'm not an expert on this, but I think often when you try to compute Gromov-Witten invariants, what the first step you do, you find the relevant curves.
Yes.
And then you say, okay, well, Gromov-Witten invariance doesn't actually count curves, it counts these maps. But then you say, well, actually every map actually has an image which is a curve. So once I know all the curves, now I have to compute the Gromov-Witten contributions by looking at all possible maps that factor through that curve.
Yeah,
And that
so
usually involves some computation of the obstruction bundle and the virtual Euler characteristic and integrating them. But if you already know curves, then because the primitive invariant is just literally the number of curves, you're done at this step. You don't even have to compute the contribution to the Gromov-Witten invariant.
Yes, exactly.
So I would imagine that whatever techniques you're using to compute Gromov-Witten invariants, you would be able to use here as well. I just don't think it's like a very interesting setup, right? When you have these primitive curves, it's a very restrictive condition. But I mean, certainly there are. So actually, I should say that there was work earlier of Zinger. Yeah, I think I'm sorry, I should have said that earlier. So this B, this was independent, was proved earlier by Zinger. So really, I think maybe I shouldn't have put both of these together. I think really what I wanted to state was theorem A, and this was like a corollary. I wasn't trying to say that this is some kind of new info. This was done much earlier by Zinger, just using the standard techniques of Gromov-Witten theory. And he, in fact, computes it in many cases and relates them to other things. So yeah, I think I should have been clear about this part. So I'm sorry about that.
Yeah, thanks.
Yes, this is really, the B is really just a corollary of A. So the main content I wanted to say was A. And this is related to these Gopa-Kumar-Vacha invariants, because in fact, you can show that, I didn't say, but these primitive counts are special cases of the BPS invariants that, you know, were the content of this digression, but I didn't really talk about this much. I think I prepared too many things to talk about, sorry.
Any other questions? Okay, if not, I just wanted to clarify something. So this counts of this ADHM vortices which you're doing is done to kind of take care of the multiple cover problem, like a sequence of curves has curves collapsing to a multiple cover, but it does not. It's not to take care of the genus issue, right?
You mean the ghost collapse?
Yes, yeah.
Yes, so the ghost collapse you have to rule out independently, and that's actually a big difficulty in this theory because, well, I could talk more about this, but the ghost you have to always rule out independently, but somehow the collapse to ghost you expect, when you do this theory, you look at generic J and then you can look at the generic path of J's. So you only care about the most generic collapse phenomena. And indeed, the collapse to multiple cover is a codimension 1 phenomenon, meaning that you don't see it, you don't see collapse to multiple cover for a generic J, but you see it along a generic path. But the collapse to, I think, I would conjecture that the collapse to a ghost is higher codimension. And in some cases we can prove it, and I don't think we can prove it in all cases, but it's expected not to be seen in one parameter families of J's. And another way genus enters here is that in this PT invariant, the PT invariant is agnostic to genus. So it should not have, because these guys mix different genera. So here, unlike in the Gromov-Wheeler invariant, you don't put G. And this is consistent with how this is done in algebraic geometry, that you really look at sheaves, and sheaves don't have genus. So you really just look at the homology class of the sheaf.
Thank you. So if there is no other questions, let's thank the speaker again.
Thank you very much. Thank you for the opportunity to speak and participate.